Yeah, welcome. So the topic we'll be discussing from this lecture is about modern computer architectures. So let us start discussing about modern computer architectures. So to start with, we'll we'll try to understand Moore's law. See, Moore's law is a famous law which you might have been heard. The performance of the computer is is increasing at a phenomenal rate over the past 5 decades, and this performance improvement is captured by a scientist called Morse, and he has stated a law, and that law is called as Moore's law. And Moore's law states that the transistors that were used per square inch of a IC integrated circuit will double every 18 months. Okay, so basically, Morse is a scientist. He has foreseen that the number of transistors that will be used in a chip in an integrated circuit will double. Roughly it will double in every 18 months, right? So it is not a it is basically a prediction. It is basically a prediction, and this prediction is true for the past 50 years, right? Suppose suppose if this prediction were true in case of commercial aircrafts. Suppose if these predictions were true in case of commercial aircrafts, then we will be having flights which are flying at the rate of 1,000 times the speed of the supersonic speed, and we'll be having aircrafts of the size of a small chair. So so basically this is an example to compare, like, how much the performance of the processor is being increased over the past 5 decades. So the number of transistors that we are using in a chip, we are doubling for every 18 months. And and for example, if the commercial aircraft is improving at that rate, then then we'll be having flights which is flying at 1,000 times faster when compared with the original flights which were designed 50 years back. And also we'll be having flights which is of the size of a chair. Okay, and also the cost of these flights will cost only several thousand rupees. So so basically we are comparing, like, at what rate the performance of the performance of the processor is increasing over the past 5 decades, right? So Moore's law is working fine for a long period of time, and that is captured in this graph. Okay, so here what you can so this is the year, right? 1975 to 1995, or say up to 2000. And this it represents the number of transistors, that are placed inside the IC. So the first processor, the first microprocessor introduced was 4004, and then 808 8080. So this 8080 processor, it has, if you see, it has the number of transistors that were used in 8080 processor, it is close to 10,000. The number of uh, transistor used in 404, it may be 2000, maybe it may be 2000. Okay, something like that, right? So and the number of transistor used in 8086, it is around 11k. The number of processor used in 80286 is 100k. The number of transistor used in 80386 is maybe 120k, so on and so forth. So here you can see around, so this may be some 1880, 1982 or 83. So in 1982 it is using it's using 100k transistors, but in 80386, here it is 1 million. So it's 1 million, right? So 80386 is not 120, probably it will be close to 200k. Probably it is close to 200 k transistors. So the point is the number of transistors that we use is actually doubling every 2 years, literally, right? So so this is what the Moore's law states. The processor performance, the performance of the processor will double roughly every 2 years, and the memory capacity, it will it will uh, it will double roughly for every 18 months, right? The performance of the processor will will improve twice in every 2 years. Similarly, the memory capacity will will improve double for every 18 months, right? So Moore's law is not only about the density of the transistors. That is, it is not only talking about the number of transistors that we pack in the chip. It does not only says that we can keep more and more transistors, but it also says that there will be improvement in the performance also. But it also talks about the density of transistor at which the cost per transistor is the lowest. So 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 it's not only just packing more and more transistors, but the cost is also reduced. But the cost will also reduce. Say say for example, currently you are creating a processor, right, with say 100k transistors, right, in a particular year. Say the cost of this processor is 5,000 rupees. Now after 2 years in the same IC, we can pack 200k transistors. Now the cost of this processor also will be 500 rupees only, 5,000 rupees only. It will not be more than that. So so that's what this point says. So the density of the transistor at which the cost per transistor uh, will also be reduced. So we are not only just packing more transistors inside the chip, but also the cost will be reduced at that rate, right? So the cost of IC, the integrated circuit cost, is calculated based on all these things. It is calculated based on die cost, the testing cost, packaging cost, and final test yield cost. What is this final test yield cost? The final test yield cost is, uh, see, die is the material, die is the semiconductor material on which the integrated circuit, the transistors, all these things will be placed, right? And after placing, you have to test it. So when you test, no, some of the die may fail. Some of the die may fail. It may not work. Only some of the dies will pass through the test. So whichever the dice that is passing through the test, that is called as final test yield. So the IC cost is calculated like this: die cost plus testing cost plus packaging cost divided by final test yield, right? So so this diagram basically it, it it shows the wafer. The wafer is the one on which the integrated circuit is placed. So basically, wafer is a semiconductor device. It's a semiconductor material, right? So here, the semiconductor material silicon is in the furnace. So first from the furnace we are taking, and then we slice into wafers, right? So it is a furnace. So in the furnace, it will be something like a molten state, and then we will take it out, we will cut it into several slices, and these individual slices are called as wafers. And on these wafers, the transistors will be placed. Okay. So this is what previously we discussed. IC cost is calculated as die cost plus testing cost plus packaging cost divided by final test yield. And again, this die cost is calculated like this: die cost is equal to wafer cost divided by dies per wafer. Okay, dies per wafer into die yield, right? So on the wafer, so this is the wafer, this is the wafer. On the wafer, we keep something called as die, right? But 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 not all dies will be successful. Only few dies will be successful. This entire thing is wafer. On the on the wafer, we are going to keep dies. So 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 only few wafers with dies will be coming out successfully. Remaining remaining it may not be successful, right? So whichever the part which is coming out successful, that is called as die yield, right? So here the green portion represents the die with wafer which is coming out successfully, right? So what is final test yield? Final test yield is the fraction of packaged dies which pass the final testing stage, right? And die yield is fraction of good dies on a wafer. Okay, how many fraction of good dies on a wafer? That is what is called as die yield. The final test yield is this is so so this step comes before this step. Okay, first this step comes, then this step comes. So initially you have die. On the die, sorry, initially you have wafer. On the wafer we are placing die, but not all the wafers will be successful. Only a fraction of the wafers will be placed successfully. Whichever the fraction which is being placed successfully on the die, that is called as die yield, right? But again, after that it should go for testing. So after testing, whichever is coming successful, that is called as final test yield, right? So this graph basically it shows it projects like how many transistors were placed on a how many transistors were placed in a chip for over a period of time. So here we are comparing basically the different. Basically here we are talking about Intel Intel processors. We are talking about Intel processor. So this yellow line it represents various microprocessor, the Intel microprocessor, and the red line it represents the memory capacity. So Moore's law is applicable for processor performance and also for memory capacity. So you can see in 1970, around 1970, the first microprocessor introduced is 4004, 4004. The number of transistor it has is around 1000, 10 to the power 3. And 8080, it has around 10 to the power 4 processor. 8086, it has around 10 to the power, close to 10 to the power 5, right? 80286, it has around somewhere between 10 to the power 5 and 10 to the power 6, so on and so forth. The various processor, how many transistors were placed. So this is number of transistors per die, number of transistors per die. Okay, so the graph similarly plots up to Pentium 2, 3, 4 up to Titanium processors. The red one shows the amount of memory. So so in case of 404, the amount of memory is 1 kilobyte, right? In case of 8080, the amount of memory is 4 kilobytes. 8086, 64 kilobyte, 256 kilobytes, no? So it's actually it's doubling. So you can see the year difference. This is 1970. This is this is around 19. This is around 1970. This is around 19, say 72 or 73. So it's around 3 years. In 3 years, it has not only just double, it is more than double, right? This is 1973 means this is somewhere around 1976. Okay, so so every 2 years it will double, right? So after 2 years it will become, it should it is supposed to become six. So this is 16K, right? This is 16K. It's supposed to become 32K, but it has here it has, this is 404, this is 80, this is 8086, this is 80286, right? Okay, so basically that's what this plot says, right? And so basically it says that the processor performance is doubling roughly for every 2 years, and the memory capacity is doubling roughly for every 18 months, right? And this line it represents the projection. So it's a projected plot, like how the uh, the processor performance or memory capacity is increasing over a period of time. Okay, right. So again, this is also the same plot of various different processors. Okay, so this plot it considers only about Intel processor, whereas this includes all other processor also, all for Power PC, IBM computers. So how the performance of these computers were increasing over a period of time, right? So how this performance improvement is happening? So basically this performance improvement is happening because of three reasons. First is because of technology, because now we are keeping more transistors in a chip, and because of faster logic. So the processor is able to work at a faster rate, right? And not only that, because also there is also another reason, because of the way of implementation, or the way in which the processor is organized. So there is something called as pipeline. With pipelines also the performance can be increased. So what is pipelining we'll be discussing later. And also by executing more instructions parallelly. So if you have more functional units, then the instructions can be more than one instruction can be executed at the same time. And also by using different instruction set architecture, which is called as RISC architecture. By using RISC architecture, we'll be using hardwired control. So as we have already discussed, with hardwired control, the more instructions can be executed, right? So that's so with all these things, basically the performance increment happens. So all these things contributes for the performance improvement. Technology, pipelining, parallel processing, and using of RISC instruction set by hardwired control unit. Okay, and also compiler technology. By using an optimized compiler, also the performance will improve. Right? And till 1980s, most of the performance improvement were coming from innovations in manufacturing technologies. So basically that the credit should go to VLSI. By that we are able to reduce the feature size. Feature size in the sense the size of the chip, the size of the chip. So till 1980s, this is the case. The VLSI was advancing at a greater speed, and as a result, we are able to pack more and more transistors in a single chip, and also the chip size is getting reduced at a greater rate. But after 1980s, the improvement is in performance is not much due to the improvement in manufacturing technology. Rather, rather, rather it is due to some other factor, right? Improvements due to innovations in manufacturing technologies have slowed down since 1980s. So after 1980s, the improvement in the performance cannot be contributed greatly towards manufacturing technologies performance, right? Mm, right. So after 1980s, then how the performance is increasing. So it is so after 1980s, actually the performance improvement uh, is because of basically the RISC instruction set and other things. Okay. So with uh, if the manufacturing technologies innovation happens in the manufacturing technologies, uh, it will result in smaller feature size. Because of that, smaller feature size gives rise to increased resistance, capacitance, and propagation delays, and larger power dissipation. So basically, after 1980s, we are unable to we are unable to improve the performance by by innovation in manufacturing technology. See, everything has a threshold, right? So after 1980s, if you keep on pack more and more transistors inside the same chip, what happens? It creates other problems. It creates other problems. By you may be able to keep more transistors on the same chip, and you may be able to reduce the feature size, but it may give rise to increased resistance. It may increase the capacitance. It may increase the propagation delays, and it may lead to large power dissipation. These type of problems we started facing after 1980s. Okay, so the point is we cannot innovate on manufacturing technologies over a particular period of time. So there is a threshold on that. Okay, so again again this diagram, what it says in the sense, the feature size. how the feature size is getting reduced. So initially the feature size in the sense the size of the IC, the feature size of the IC is 60. It was 60 nanometer. It was 60. It was 60 nanometer, and over a period of time, you can see it is keep on reducing, right? So here it is a factor. At what factor? The factor was shown here, right? Okay. So 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 it is keep on reducing over a period of time, uh, from uh, from 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 60. It is reducing, and it is, and over a period of time it is reducing, right? So the feature size shrinks by 70 percentage per 18 to 24 months. So that's what's shown here in an example. So if you consider the human hair, the size of the human hair is 100 micrometer. The size of an amoeba is 15 micrometer. Red blood cell is 7 micrometer. The size of AIDS virus is 0.1 micrometer. The size of buckyball is 0.001 micrometer. Like that, the feature size of the transistor is getting reduced over a period of time. But if you, but here you can see even if you reduce the feature size over beyond a certain point, again what happens in the sense, it may create other issues. It may increase the resistance, capacitance, propagation delay, and it may lead to higher power dissipation. Okay, right? So that this diagram represents the transistor costs per year. So this represents the dollar, the cost of the transistor in dollar, and this represents the feature size. This represents the feature size. Okay, so you can see as the year goes on, the feature size is as the year goes on, the cost of the transistor per year is gradually decreasing. Okay, the cost is decreasing. This is year, this is basically year 68 70. This is year, sorry. Okay, so here also this is year. I have mentioned this as feature size. Feature size is basically this. Y-axis represents the feature size, x-axis represents the year. This is 60, 1960, 1965, so on and so forth. This is feature size. So in 1960 the feature size is close to 100 nanometer, but in 1970s if you see, it is close to 10 nanometer. In 1980s, it is close to 1 nanometer. Like that, it is decreasing. Similarly, this diagram, it shows the cost. The cost of uh, the cost of transistor in 1968 is it's close to $1, whereas in 1974 it is close to $0.1, so on and so forth. So the transistor cost is also decreasing at a greater rate. Okay, right? But what about the power consumption? See, actually the power consumption is increasing. So this is from 386 processor. If you see, the power consumption is increasing, but you cannot increase the power consumption beyond a certain point. You cannot allow the power consumption to exceed a certain point. We cannot go allow the power consumption to go beyond 100 watts. So if you see, we have here we reached a saturation point at Pentium 3 or Pentium 4. The power consumption should be at this range only. You cannot go beyond that. Okay. Right. So here is a YouTube video. This I will be showing in the class. It shows like if the power consumption exceeds a particular limit, then what will happen? If there is no heat sink, then what happens to the processor? That's what this video shows, right? And the power consumption is basically calculated based on these two factors. Power is calculated as dynamic power plus leakage power. Dynamic power is the actual power. Dynamic power is the actual power, which is nothing but the number of transistors into capacitance, into voltage, into frequency, right? It is in a particular transistor, how many transistors you are using, how many capacitance you are using, the voltage square into frequency. The leakage power is so this is something called as see, in any circuit there will be some power leakage. In any circuit there will be some power leakage. So So that happens with the microprocessor also. So there will be some power leakage, but over a period of time, this power leakage is rising, and this power leakage, it will soon match the dynamic power. That is, the leakage power will become close to the dynamic power. So if you see the various Pentium processors, the various Pentium, the original first Pentium processor in the year 1993, the number of transistors used is 3.1 million transistors. Its clock speed is 60 megahertz. Pentium Pro, which is introduced in 95, the number of transistors used is 5.5 million, and the clock speed is 200 megahertz, so on and so forth. In Pentium 4, which is released in 2000, the number of transistors used is 42 million, and its clock speed is 1.5 gigahertz. Okay, so basically we are saying like, so all this, it talks about the Moore's law only, and also it talks about the power dissipation. Okay, so dynamic power is basically given by this equation. Dynamic power is roughly equal to what are the various units you are using, and for each of the units you have something called as K, right? C, V, A, and F, right? C represents the capacitance of the circuit, and V represents the supply voltage, A represents the activity factor, and F represents the frequency. Okay, so basically it's a multiplication of all these things, and for each unit you should know what is its capacitance of the circuit, and what is the voltage, and what is the activity factor, and what is the frequency. Multiply all that. This K is some constant. With that you multiply and then sum up that for all the units. So by that we can roughly calculate the amount of dynamic power. Okay, so this what it shows in the sense, C is constant, C won't change, but V and A will change. V and A will change. F will not change much. Okay. Right. So yeah. So till recently, most desktop processors were fabricated using 65 nanometer process. That is, this is the feature size. The most of the processors feature size is 65 nanometer. So Intel in January 2007, they demonstrated a particular IC whose size is only 45 nanometer. Whose size is only 45 nanometer. A decade ago, chips were built using 500 nanometer. 500 nanometer is otherwise called as 0.5 micron, right? In 1971, the size of the transistor, I mean the size of the, what you call, the future size of the chip is 10 micron. Okay, 10 micron means it is 10,000 nanometer, right? It is 10,000 nanometer, right? But a decade ago, it is 500 nanometer, right? At before 2007, it is 65 nanometer. In 2007, it is 45 nanometer. So basically, this shows like how the future size is decreasing over a period of time, right? So since 1980s, most of the performance improvements have come from architectural and organization innovation, right? So up to 1980s, performance improvement came from where? In manufacturing innovation. But after 1980s, performance improvement has come from architectural and organization innovation. So what is the difference between architecture and organization? So, so that, so I think we can stop here. So from this, we will continue on the next lecture. So the gist is, the Moore's law has predicted the performance improvements of the processor, and also the memory capacity will be doubling every 2 years. That is, the processor performance will be doubling every 2 years, and the memory capacity will be roughly doubling every 18 months. Since 1980s, this performance improvements came from manufacturing process. But after 1980s, this performance improvement is basically because of architectural and organizational innovation. So let us stop here for today's session. We'll continue further in the next lecture. Thank you.